Okay, now I want to talk about the ultimate data structure for the disjoint set abstract data type. And it's called union find. And so I guess you know that it's got to be pretty legit because its name is actually the two operations in the entire abstract data type. Okay, so it's simply called union find. And so we're going to build it up and kind of improve it a little bit at a time, just like we did with the other algorithms. So union find, like the very last one we looked at, it's going to have a single list. But the IDs of the elements are fixed. Okay, so what's the use of that if nothing ever changed? Well, the list isn't going to store the IDs of the elements. The list is going to store something a little different. So it's actually going to be a list of what I'll call parents. So it's actually going to store an arrow or a pointer to another bubble. Okay. So I'm not going to think about merging the bubbles as much as I'm going to think about bubbles being connected to each other by an arrow. And so I'm saying, which bubble is this connected to? Well, first, all the bubbles are just connected to themselves. But let's see what happens when we run a union. Okay. So what I'll say is, for union 0, 2, well, I'll say the second one here, which is 2, will actually point up to the first one, which is 0. So let me grab my little arrow over here. Okay, so now 2 is going to point to 0. And so I'll update my parents list accordingly. So 2 points to 0, no longer 2. So there we go. All right, cool. So let's just keep going like this. So if I do union 1, 8, well, 8 is now not going to point to itself, but it's going to point to 1. There we go. Okay, now union 7, 8. Okay, now this is interesting. You know, the computers are dumb. They're always going to do the same thing. So I said, have 8 take on 7. But that's not really what I want here, right? Because, I mean, 8 points to 1. If I have 8 take on 7, I've sort of lost the fact that 8 and 1 really should be connected. So let me do something a little different. Instead of having 8 point to 7, I'm actually going to have 1 point to 7. So I'll have the parent of 8 point to 7. Okay, so I'll make this systematic in pseudocode in a moment, but I just wanted to show you, you know, I can't just do exactly what I'd done before because I'll lose some of the connected information. Okay. Did I remember to update? Okay, I guess I'm saying, okay, this was after I did union 0, 2, after I did union 1, 8, then 8 pointed to 1, right? And then after I did union 7, 8, well, I said that in that case, nothing changes except for 1 now points to 7. And 7 actually still points to itself. Okay, I didn't mean to get rid of that arrow. All right, so 1 points to 7. That's the only thing that's changed. Okay, let's keep going just to get a feel for sort of how we're going to build this thing. So let me just keep going with the same example that we've been looking at. Okay, so union 1, 6. Well, that's saying that 6 should no longer point to 6. It should actually point to 1. So here's where we get slightly more interesting topology. Topology is how things are connected. So now 6 is going to point to 1. I need a better arrow than that. Okay, 6 is going to point to 1. There we go. Get my nice, this is Inkscape for you. Get my nice fill and stroke here. Make sure I get that to be an arrow. Okay. Nice. So cool. Now it's starting to look a little different. Notice that this is not just, before I thought that maybe this was just going to be a linked list, but now I see it's not that simple, because 6 can actually point to 1, but 8 also points to 1. This is going to create something called a DAG, Directed Acyclic Graph, which we'll certainly talk about more in the course. But really, altogether, this is creating what I would call a forest, or a DAG forest. These are really trees of sorts. If I flip the arrows, those might look like trees that you've seen before, where each node has children. Instead of thinking children, we're thinking parents. So we're already doing trees, and we're doing even more general. We're doing forests, so collection of trees. Okay. So, but we're able to store this whole tree just with a single list, and so that's pretty neat. Our data structure is just a list that we think, interpret in a special way. So here I just made 6 point to 1, and that's all that changed. Okay, so I don't really have to change much. So that's your first hint that maybe this is a little more efficient. You don't really have to change a whole lot to represent the merge events here. Okay, now what about 0 and 1? So that's the last one for now. And then I want to write a little bit of pseudocode to describe what I was actually doing this whole time. Okay, so that's saying 1 should now point to 0. But remember, if 1 already points to something else, then I keep going until that something else points to itself. Whoops, I got rid of this self loop on 7 again. I didn't mean to do that. Okay, so 7 is still pointing to itself. So I just keep following the arrows until I get to something that points to itself, and that's the thing that I'm going to merge here. So start at 1. 1 does not point to itself. Follow the arrow, get to 7. 7 does point to itself. So that's the thing that I'm going to have a parent of 0 here. Okay, so let me draw an arrow. Having a bit of trouble with these arrows. Okay. All right. So you see, much like we had before when we were drawing the bubbles, you can see that all the things are connected to each other that have merged. Okay. So let's write a little bit of pseudocode. Let me make way for that here. So the first, there's a helper function I'm going to make, and it's going to be called root. And it's going to do the thing that I just said, basically. So if I say root I, so this is just pseudocode. I generally shouldn't change parameters, but I'm going to change I here as I go, just to make it simpler to describe. So I'll say while parent of I is not I is equal to parent I, return I. Okay, so let's see what this does. Let's actually go ahead and just, maybe we'll look pretty far down here. So for example, if down here I said root 6. Okay, so I see that, what's the parent of 6? Well, 6 points to 1, right? Okay, so 1 is not equal to 6, so I have to keep going. So I say I is equal to, so I starts off as 6, then I takes on 1, so this is parent of 6. Okay, so now we say, is parent of 1 equal to 1? No, the parent of 1 is 7, right? Okay, so now we make I is equal to 7, which is the parent of 1. So first we followed this arrow up to 1, now we followed this arrow up to 7. What about the parent of 7? Well, the parent of 7 is 1. 0, 1, 2, 3, 4, 5, 6, 7. I forgot to update this. The parent of 7, whoops, this is actually the list I'm supposed to be looking at. This list is updated. The parent of 7 is 1. So sanity check here. or I'm sorry, the parent of 7 is 0. Okay, let's check. So 0 should have 3 things pointing to it. 0 itself, 2 and 7, 0, 2, 7. Okay, that looks right. 1 should have 2 things pointing to it, 8 and 6. And I see that. Yep, okay, I think I got this right. This is why you normally have the computer do it, because humans are so prone to error. Okay. But anyway, so now I'm at, okay, so 7, parent of 7 is 0, which is not 7, so I got to keep going. So that's the parent of 7. And finally, the parent of 0 is 0. Okay, so the root of 6, therefore, root of 6 is going to be 0. But look, visually, you're just walking to the root of this tree, to the top of it, when you can't go anymore. So I go, follow the arrow. It's just 6, 1, 7, 0, boom, I'm done. Okay, so that's the root function. Now, to see if two things are in the same connected component, if they're in the same bubble, what do you think you should do then? Okay, so the find operation actually just uses root as a helper function. So our first version of find could simply be return root I equals root j. All right. So if they share a root, then they must belong to the same bubble. So let's see. If I do a find of 1 and 2, okay, so 1, follow the arrows up, root is 0. 2, follow the arrows up, root is 0. Very good. All right. So that seems like it's going to work. Okay. And if, by contrast, if I do find 5, 7, okay, well, the root of 5 is 5. The root of 7 is 0. Those are not equal, so they're not in the same component. Okay, so it seems like we've got down our root, or it seems like we've got down our find now. What about the union? How do I actually put these together following this rule? Okay, so let's see. So if I say union ij, so what I'll say is, okay, root I is equal to root I, root j, so I'll just store these in temporary variables so I don't have to redo computation. That's my whole memory time trade-off. Okay, so if they have different roots, then I need to merge them. Otherwise, I don't need to do anything. So for example, if I called union on 8, 6 at this point, I wouldn't need to do anything because they're already connected together. They've got the same root. But if I said, actually, let's back up to this step. If I'm down here and I said union 0, 1, well, 0's root is 0, 1's root is 7. Those are not the same. I would have to actually do something. So let me move this down a moment so we can think about, we can check how we got here. So if the root of I is not equal to the root of j, then we have to do a merge. So what we should do is simply say, well, we can say that the parent of root j is root I. Let's see. Does that do what we thought it would do? Let's just kind of check as we go along here. So, okay, I said union 0, 2. So at this point, before I said union 0, 2, 0's parent was 0, 2's parent was 2. Okay, so yeah, so they're their own roots. So they're not equal. So I said the parent of root j, which is 2, should be 0. Okay, that checks out. Just get a similar thing with 1, 8. What about this? This is where it starts to get a little more complicated. So, okay, when I go, at this point, when I go to say union 7, 8, I see that 7's root is 7. Sorry, I'm here. I'm about to do union 7, 8. So 7's root is 7. 8's root is 1. So I want to say that, okay, so 8 is j. So I want to say that the parent of the root of j, which is 1. So the parent of 1 is equal to the root of I, and I is 7. Okay, cool. So that did my 7. Now I'm here, and I want to do a union 1, 6. So 1's root at this point is 7. 6's root is 6. So I say, okay, 6's parent should be 1. I got it. Okay. And now finally, when I do union 0, 1, I say, okay, I say 1's parent is 7. 0's parent 0, so 7 points to 0. And that's what we got here. All right, so here's our first version of union find. And we'll improve on this on Wednesday. But something I want to point out about this, you know, it's definitely, it's awesome. Okay, so we only have to store one list, and it seems like we don't really have to change that much, right? Before, when we had a list where every element stored an ID of the bubble we were in, we had to change a whole bunch of elements, right? So this is kind of cool. Seems like we're only changing one element each time, so that's efficient. But you can run into a problem if I do this. Let me show you a problem case. So let's just look at another example. So if I have this kind of sequence, if I say union 0, 1, and then I say, okay, so that gets me, let me think how I can get this here. So I say union 0, 1, let's see, how can I get this case? I'm trying to come up with a case where I basically, instead of a nice tree, I end up with a big long linked list. Well, actually, maybe that's a good thing to think about. We can get back to that. We can think about what's a case where we would get one long linked list, and then it would take kind of a long time to walk up to the root when doing a find. Okay. So this is where we're going to pick up in class, and we'll think about this and then implement some of it. Okay.